And there we go. All right, guys. So today what we're going to do is we are going to spend the entire day figuring out the order that the periodic table is put together. This is going to start gently. This is going to start casually. And this is going to get really mental really fast. So guys, don't get lulled into thinking, oh my gosh, I got this all figured out. Because this is going to get a little deep by the end of the day. So guys, to make you successful, here's what you need to do. Ready? Check this out. Oh my gosh, it's your piece of paper. Huh? There. I'd like to point out that line is actually red. Not bad. I know. All right, so guys, here's what you're going to do. You are going to draw yourself a skeletal periodic table. Notice the way that this works. It does not extend down to the midpoint hole in your paper. It goes down about 2/3 of the way between the first and second hole. Notice that you have a fair amount of white space to the left of this, but it is still large enough that you can write in the S and the P sublevels that we have broken up into 2 and then 6 columns. Then, guys, what you're going to do is you are going to skip down 6 lines, not 5, not 7. You are going to skip 6 lines, and then you are going to draw in the F sublevel. This should be drawn to scale. You should be protecting space to the left of your table, and then the space directly beneath the body of the periodic table, realizing we're just going to put the F sublevel not where it truly belongs, but we're skipping down some space. How about this for helping you be organized? You guys ready to go? What are you doing?
I drew it too big.
I'm wondering, yeah, you'll still be okay. So guys, I know you've probably figured this out by now, but the reason that we're protecting this space and the reason that we're protecting this space is that's where you're going to be taking the really important notes, if you will, that you're going to be writing down today. So that space below and that space to the left is really important. Functionally, what you're going to be doing is you're going to be drawing a bunch of arrows. You may find that that may not be big enough if you want another sheet of paper. Okay, so guys, can I assume that we're all relatively pulled together here? Not yet. Good heavens. All right, I'll be up here if you need me. Oh, no. Good. What's that? That'd be a nice touch. Yeah, put my feet up. All right, guys, here's the scoop. I know that I've told you multiple times that this space is important and this space is important. Let me explain to you what you're going to be doing in this space. Guys, we're talking about trends, right? And when we talk about trends, we are talking about generalizations in terms of how the table is organized. We are going to talk today about 5 trends on the periodic table. So eventually what you're going to have, don't do this now, but eventually, guys, you're going to have 5 downward pointing arrows over here on the left. And we're going to talk about what are the trends as we go down the groups on the periodic table. Then you're going to have 5 rightward pointing arrows beneath in this space. That's why we skipped 6 to give you a little room. We're going to have 5 arrows pointing here, talking about the trends as we go across periods. Now guys, this space down here, this is where, don't write this down obviously, this is where you're going to take notes, because the way this is going to work out is we are going to define something you need to know about the periodic table. The definitions will go down here, then the trends will go in these spaces. Can you sort of see how this is going to play out over the morning? Okay, so guys, here we go. I'm assuming you're caught up. And guys, what we're going to do now is we are going to zoom in to the body of the table. Now notice what I did is I brought the F sublevel up, and that's fine. So before we start talking trends, the first thing we're going to do is label the periodic table. Guys, there's parts of this that you need to know the names of. So what you're going to see is these notes are going to come up right here. But this isn't where you're going to write them down, right? Where are you going to write them down? Down below the F's. So guys, the first terms that you need to know about the periodic table are the terms that we use for the vertical columns and the horizontal groups. So guys, let's go horizontal first. So write down the word periods. And that goes down below the F. This is a term you need to know. So guys, periods are the horizontal rows on the periodic table. Now let's see what you learned from the last unit. How many periods are on the periodic table? There's 7, and what do they relate to? The energy levels, right? So there's 7 periods, 7 energy levels. They're the horizontal rows. Is that okay? Okay, now guys, we've got the vertical columns, and these are called groups. The groups are the vertical columns on the periodic table. This is a tricky question. I'll bet you'll get it though. Guys, if the periods are the horizontal rows, and there are 7 of them, they're the energy levels, now that we're thinking about vertical groups, guys, what do all the elements in a group? So what do all these elements have in common? What do all these elements have in common? What do all the elements in a group have in common, Maddie? Bingo, same number of valence electrons. Guess what that means? They all react the same. Guys, all the elements in a vertical group all react the same because they have the same number of valence electrons. We're going to look more at that later. You guys good to go? Periods, horizontal, groups, vertical? Okay. Now guys, the next thing you need to know is every single one of these groups has a name. We're not going to name all of them, but we are going to name some of them. And guys, the ones that I give you are the names that you need to know. So thinking about the names of these groups, the first thing we're going to do is number them. And remember what Maddie told us. What do all the elements in a group have in common? Same number of valence electrons. So guys, we are going to number the groups 1 through 8, because what do those numbers tell us? The number of valence electrons. So number them 1 to 8. Notice, guys, we're skipping the D sublevel. Why are we doing that? They're not valence. But guys, if you look at your periodic table, you'll notice that it does this for you. But they number, well, sort of. If you look at the stuff on your periodic table, you'll notice that it goes 1, 2, but then it goes 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 through 18. So if you look at the Arabic numerals, they include the D's. But guys, if you look at the Roman numerals, it's Roman numeral 1, Roman numeral 2, Roman numeral 3, 4, 5, 6, 7, and 8. So they do this with the Roman numerals, but we're just going to do it with the Arabic numerals. All right, so guys, here we go. Names of the groups. Ready? You don't need to know them all. You just need to know 1 and 2 and 7 and 8. But you guys already know number 8, right? Noble gases. We'll get there in a second. So guys, group number 1. Well, we'll do the noble gases now. So guys, group number 8 are the noble gases. That one you already knew. Now we just got to do 1 and 2 and 7. So guys, group number 1. These are what are called the alkali metals. So it's Alkali. So this first group are what are called the alkali metals. So lithium down through sodium, potassium, rubidium, cesium, those are what are called the alkali metals. Yeah? I don't know. That's an interesting question. Alkaline means basic. So there's acids and there's bases, and initially, that's probably where it came from, because initially, it turns out that when you put these metals in water, they turn into bases. Never put that together. So I don't know why they called alkali base, but that's the connection. All of these in water form bases, the opposite of acids. So guys, these are the alkali metals. Their neighbors to the right in group number 2 are what are called the alkaline earth metals. And guys, if you can fit it in, add the word metal. You're going to find out in a minute everything on the left-hand side of the periodic table is a metal, so it's a little redundant. So if you just call those the alkaline earths, that's fine. But technically, they're the alkaline earth metals. All right, so guys, we got group 1, the alkali metals, group 2, the alkaline earth metals, group 8, which is the noble gases, and then guys, group 7 is the last group that you need to know. And group number 7, well, actually, you know what? It's not technically a group, but we'll do this one first. So guys, while this is not a group, the D sublevel, together we give a name. So let's do that first, then we'll go to group 7. So guys, understand that this is not one group, this is all 10 of the groups in the D sublevel. These are what are called the transition metals. So guys, everything in the D sublevel are what are called transition metals. The idea is that they transition from the S's to the P's. They're not valence, they're just something we're moving through, and that would be where the name transition came from. So we've got these, all of the D's are the transition metals. Then guys, group 7, these are what are called the halogens. Maybe you've heard of them for a while there. Halogen headlights in cars used to be sort of the cutting edge in terms of really bright white lights. Now they're doing things with xenon and LEDs and things like that. But we used to make headlights out of these. Not so much anymore. But you can still buy halogen bulbs, like for reading lights and things like that. All right, so we've got the alkali metals, the alkaline earth metals, the transition metals, the halogens, the noble gases. You guys all caught up? Okay, so guys, the last thing that we need to do then, and we're done with the secretarial stuff, is we need to name the F sublevel. And understand this is not a group, it's technically horizontal, it's sort of like a part of a period, but these parts have names as well. So let me show you how this works. So guys, which sublevel is this down here? The 4F. But you understand that it actually belongs in between here. It goes 55, 56, 57, 58. So this entire 4F should be right here. So when they named it, what they did is they anchored it back to the periodic table. So this comes after lanthanum. So what they did is they call these the lanthanoids. It tells you where they tie back to the periodic table. So guys, if you understand the logic that the lanthanoids come after lanthanum, then what's the name of the 5F going to be? So it comes after actinium, so they are called the actinoids, not the actiniumoids. They're called the actinoids. All right, so there you got it, guys. You now understand that groups go up and down, same number of valence electrons. Periods go left and right. They are the energy levels. You now know that the alkali metals are group 1, the alkaline earths are group 2, the transition metals are the D sublevel, the halogens are group 7, the noble gases are group 8, then you got the lanthanoids and the actinoids. You guys all caught up? You're good? All right, zoom out. Here we go. So guys, we are now going to talk trends on the periodic table. There's 5 of them that we're going to do. This is the way this is going to roll out. Guys, the first thing I'm going to do is I'm going to identify for you the trend we're going to talk about. That's going to pop up right here. Chances are good the first couple you're not going to need to write down the definition for, but then guys, we're going to fly in some arrows and we're going to identify what the trends are. You ready to go? Here we go. So guys, first of all, atomic number. If you feel like you need to write this down because you don't remember that the atomic number is abbreviated Z and it's the number of protons in the nucleus, you can write that down here. Don't write it down up here, right? Write it down at the bottom. So guys, atomic number is the number of protons in the nucleus, if you don't remember, and it's abbreviated Z. Remembering that? Okay, so here's what you're going to do. Fly in 2 arrows. Guys, do that right now. You're going to do a down pointing arrow and you're going to do a right pointing arrow. And guys, then what you're going to do is you're going to label that arrow, those arrows, Z. So put a Z at the top, put a Z at the left. And guys, remember, eventually there's going to be 5 arrows to the left and 5 arrows below, so conserve space. All right, now it's time. Grab your periodic tables. And guys, this is probably unnecessary, but we're developing some skills. So guys, where on the periodic table is the atomic number? We're going to pretend like we don't know. So if we don't know, we go down here to the key. The key tells us that the atomic number is in the upper left-hand corner. And now we're going to find the trends. You ready? Allow your eye to scan down the groups. And as we go down a group, what happens to the atomic number? Do the numbers get bigger or do they get smaller? They get bigger, right? So guys, down a group, and we're going to write this in on our arrows, down a group, it goes from smaller to larger. Now, are there any exceptions to that trend? Can you find anywhere on the periodic table where you go down a group and the atomic number gets smaller? Well, yeah, but the F actually belongs up here though, right? This isn't its own period. So guys, any examples of where it gets smaller? None. It always gets larger. But guys, does it get larger sequentially? 1, 2, 3, 4, 5. No, it's hopping all over the place, right? But it does get bigger. So now guys, what about this? Left to right. Now allow your eye to scan across the periods. Notice I use that term correctly. Allow your eye to scan across the periods. What happens to the numbers? Do they get bigger or smaller? Bigger, right? So left to right, we're going to go right here, we're going to go smaller. Over here, we're going to go larger. And guys, the trend from left to right is smaller to larger. Now, are there any exceptions to that trend? There are none. You get the idea? Okay, so now guys, here's what you've done. You have figured out how, using your periodic table, to identify trends in groups and periods by simply scanning down the groups across the periods and identifying what happens to the numbers. You get the idea? Okay, now guys, let's do this. What is the overall trend on the periodic table? Where are the largest atomic numbers, top or bottom? Bottom, left or right? Right, so the biggest numbers are down here in the bottom right. Does that jive with what you're saying? Where are the smallest numbers? Top left. So the overall trend is from top left to bottom right. You guys good? All right. So now guys, let's do this. The next trend that we're going to do is atomic mass. If you do not remember that the atomic mass is the number of protons and neutrons in the nucleus of an atom, you can define that down below. But guys, in either case, fly in 2 more arrows. All right, now that you've got your 2 arrows, label them with the abbreviation for atomic mass, which you all remember to be the letter A. So we're going to label this A and A. Now guys, just like before, we're establishing a pattern. Let's figure out the trend in atomic mass. First we got to find where it is on the periodic table. Where's atomic mass on the periodic table? Upper right-hand corner, small red numbers. So guys, allow your eye to scan down any and all groups on the periodic table. What is the trend as you go down a group for atomic mass? Lighter to heavier. Let's write it down. It goes lighter to heavier. Are there any exceptions to that? Down a group, do we see any examples of a place where we go down and they get lighter? You guys see any? Down a group where they get lighter as you go down. Do you see any? You want to know why you don't see any? Because there aren't any. They always get heavier as you go top to bottom. You guys sold on that? Okay, now guys, left to right. Allow your eye to scan left to right across the periods, and what is happening to mass? Do these get heavier or lighter as you move to the right? They get heavier, so let's write it down. So guys, these go from lighter to heavier as we go left to right. Ding. Now guys, do you see any exceptions to the trend? Go ahead. All right, let's look. So guys, if you look at uranium, uranium has an average mass of, we're down at element 92, very down at the tippy bottom. Uranium goes 238, neptunium is 237. We moved one to the right and it got lighter. Do you see other exceptions to the trend? Go ahead. Give us element numbers. 108 to 110. So 277, 268, 269, then, and it just keeps going down, doesn't it? Any other exceptions? Go ahead. Yeah, look up at like 52. Beryllium 127, iodine 126. So guys, we can stop there. There are other exceptions, but let's talk about it. Guys, first of all, what explains the exceptions to these rules? We know that as we're going to the right, we're adding protons, right? Every time we step to the right, we're adding a proton. So they should be getting heavier. So what would explain the fact that in some instances they get a little bit lighter? Fewer neutrons. Yeah. So guys, what's going on is as we step to the right, we are adding a proton, but that element to the right must have fewer neutrons, making it lighter. Do you understand the explanation? Here's then the idea, guys. Do these few isolated exceptions negate the trend? Or is the trend still valid? And guys, the answer is the trend is still valid. So you got to understand this. Guys, trends are overarching ideas. And the overarching idea is left to right, they get heavier. And we will find some exceptions to trends, but that doesn't invalidate the trend. You got the idea? Because this is about to get hard. You guys ready to go? All right. So guys, why did we fiddle around with atomic number and atomic mass? Well, guys, we did atomic number to teach you how to identify trends. We did atomic mass to make you comfortable with the idea that exceptions to trends do not invalidate the trends. You okay with those two ideas? Okay, one last thing and we're going to move forward. Guys, these get heavier as we go to the bottom. They get heavier as we go to the right. So where are the heaviest elements on the periodic table? Bottom right. These guys down here. Where are the lightest elements on the periodic table? Top left. You guys good with the ideas? All right. This one you want to write down. Guys, the last three trends that we are going to talk about can be confusing. You're going to see that I drew as many pictures for you as I possibly could. But guys, please ask questions. Here's the next trend we're going to talk about. Atomic radius. Write this down. We haven't talked about this yet. This is hard, but you can do it. All right. So guys, atomic radius. Let's talk. So guys, in order to understand atomic radius, the first thing that you've got to understand is radius. Don't write this down, but here we've got a circle, and here's the middle of the circle. Where is the radius of this circle? From the middle to the outside. So you understand, guys, from whatever math class this was presented in, this is the radius of the circle, right? And that works great for circles. But guys, in our world, circles are not circles. Circles are atoms. So if we're talking about the atomic radius, what is in the middle of an atom? The nucleus. What defines the outer edge of the atom? Valence electrons. So guys, that is actually the definition of atomic radius. It is the distance between the nucleus and the valence electron shell. Yeah? What do you mean? Oh, because they're dumbbell shaped? But remember that we've got 3 of these dumbbell shaped and the sum of those is actually a sphere. But that's actually not how we do it. It's interesting. You ready? How do they measure atomic radii? They don't actually measure the atoms. What they do is they bring 2 of these atoms together, measure the distance between the nuclei and divide by 2. Yeah, so think about it this way. If you wanted to find out my radius, what you could do is you could bump me up against you. And if you measured the distance between the middle of both of us and divided it in half, if we were the same sort of size people, you could figure out my radius by knowing that it's half the distance to you. And that's actually how they do it, is they put these atoms together in molecules and then they measure the size of the molecule and divide. Yeah, it's pretty cool. Wait, when are we going to talk about this? In the next unit, we're going to talk about how they do it. It's called X-ray crystallography, and it's really cool. All right, you guys good on atomic radius? You understand? I know you don't know the trends, but you know what it is, right? Okay, so then guys, draw in your arrows. Now what we're going to do is we're going to label these arrows. There is not an accepted abbreviation for atomic radius, so we're just going to label these arrows AR. All right, now let's talk, y'all. We are going to go down a group. We're going to go across a period. So guys, first of all, and this needs to be in your notes. Notice this is going to come in down here because you not only need to understand the trend, you need to understand the explanation. So guys, first of all, down a group. So guys, before we explain the reason for the trend, let's find the trend. So grab your periodic tables. You ready? Flip them over. Now guys, look at the key in the lower left-hand corner. And if you allow your eye to scan around the key, you will notice on the left-hand side, we are given data about the radii. But be careful, there's 2 different radii. See that one is covalent and the other is atomic? We are looking at the atomic radii. We'll talk covalent radii later. Guys, notice the units, angstroms, 10 to the negative 10th meters. Doesn't really matter, but just understand these are bitty. So where are the atomic radii? The bottom number in the shaded red box in each cell. Got it? Okay. Now, guys, allow your eye to scan down the groups and let's identify the trend. As we go down a group, are these numbers, and it could be any group, but guys, as we go down a group, are these numbers getting bigger or are they getting smaller? They are getting bigger. And guys, we will write it in a minute, but here's the deal, if you watch my hands. As we go down a group, these things get bigger. Given what you already know, why would that make sense? As we go down a group, what's happening to these atoms? But what's happening that would make them bigger? We're adding what? Well, S&P shells, but energy levels. So guys, these are periods, right? So we've got the first period, the second period, the third, the fourth, the fifth, the sixth. Guys, as we go down, we are going through periods and we are literally it's just this, right? We are literally adding layers to the onion, right? So guys, the explanation then is this. And it's down here, this increases due to additional energy levels. So guys, if that doesn't make sense, let me show you what we're talking about. And we're going to go back to the Bohr model of the atom. This should actually be the S's and the P's and things like that. But guys, check this out. So looking at group number 1. Tell me where group number 1 is. Far left. What are they called? The alkali metals. But guys, this works for any group. So this is hydrogen. That's what hydrogen looks like. 1 proton, 1 electron. So now let's go down to lithium. Well guys, lithium looks like this. And then if we go down to sodium, sodium looks like this. Can you see that as we go down a group, these are getting bigger because we're adding layers to the element? Does that make sense? Okay, so guys, if that makes sense, let's label the line. So these go from smaller to larger. Are you all comfortable with that idea? We're adding layers to the onion and the elements get bigger. Good? All right. So now, guys, down here, did you all get that smaller to larger? Okay, now do this. We're going to go back and now we're going to talk about across a period. You want to add this to your notes as well. This is going to surprise you. You're going to like the explanation though, guys. Allow your eye to scan across any period and remind yourself that you're comfortable with the idea that isolated exceptions to a trend does not mean the trend is bad. You will find exceptions. Find the trend. Guys, as we go left to right, do these numbers get bigger or smaller? Oh boy, they do. Guys, as we go left to right, these elements get smaller. So guys, let's talk about why. I'm going to get, well, I should say this first. Are you all sold on that? Are you convinced that they do get smaller? There are exceptions, but do you understand they do get smaller? Okay, so guys, this is why. Write this down and then we'll talk about it. The reason that these get smaller is due to an increased nuclear charge as protons are added to the nucleus of the atom. And guys, I'm going to show you what that means. You guys have no idea how many hours it took to put together this presentation with all the little things that move and the drawings, and it was fun to do though. Okay, so guys, are we all at least, we don't understand why, but are we sold on the idea that the atoms get smaller? Is that okay? Okay, here's why. Can I go? Okay, check it. Not yet? Okay. How about now? Okay, so guys, let's go back here. Don't write this down, obviously, but here's what we've already established. When we go down a group, these get bigger, and we're good with the idea that it's because we're adding layers, right? Okay, now let's move left to right across a period. So guys, we're going to kind of pretend, so we're going to say that helium's over here in group 2. It's really in group 8, but we're going to say it's in group 2. So guys, how is helium different than hydrogen? Well, helium's going to have how many protons? 2. Now guys, think about this. What holds the atom together? Well, the nucleus is pulling on the electrons. So guys, what nucleus is going to have a stronger pull? A nucleus with 1 proton or a nucleus with 2 protons? A 2-proton nucleus is going to have a stronger pull because it's more positive. So what happens is these 2 protons in helium pull these 2 electrons tighter together and the atom gets smaller. Does that make sense? And guys, that happens in all of these elements. So if we go to lithium, lithium has got 3 protons. If we go over to beryllium, beryllium has got 4 protons. 4 pulls harder than 3, and it brings the atom even tighter together. Now, if we go over to boron, it gets even tighter because boron's got 5 protons, and it sucks that atom even tighter together. Is that okay? Then if we go down to element number 11, that's sodium. If we go over to element 12, magnesium, now we've got 12 protons, pulls it even tighter together. We go to aluminum, even tighter together. And as we move across a period, more protons, more pull, smaller atoms. Do you buy it? So guys, and this actually, one of my students figured this out. As she was taking notes 2 years ago, she drew this on her periodic table, and I liked it so much, I asked her if I could reproduce it. This is the way she envisioned this, and it was brilliant. You ready? So well, here's your periodic table. And remember, we've got the periods, right? And this is what she drew into her notes. It was really smart. And then she came and said, is this right? So she envisioned it like this. When you go across a period, so hydrogen, helium, it gets smaller. Then when we go down to the next group, the next period, what's going to happen? As we go down, it will get bigger, and then as we move to the right, it will get smaller, like this. And then when we move down here, what's going to happen? Bigger, and then down to smaller. And bigger, and then down to smaller. So when we move down, they get bigger because we're adding layers, and as we move to the right, they get smaller because the nucleus is getting stronger. This was really cool. She did a great job with that. Guys, do you see the trends? We okay? Questions on it. This is important. Go ahead, Cap. Yes, keep going. Good. Guys, now let's draw, but the answer is yes, but let's look. So guys, draw on the trend. As we move left to right, do they go big to small or small to big? They go big to small. So they go larger to smaller. Now guys, Cat got it exactly right. If it goes larger to smaller, where are the big fatties on the periodic table? Bottom left. So francium is the largest element on the periodic table. And guys, where are the little itty bitty guys? They're in the top right. It's actually helium's the smallest, but it goes big fatties, little small dudes. That's the overall trend. Kat, that's cool you figured that out. You guys good? Okay, now guys, understand, we're not going to move forward until you're telling me you're good with this. Because guys, if you don't understand this trend in radius, the next two that we're going to do aren't going to make sense to you. So go ahead. Yes. Not, keep going. Say it again. The electrons are getting pulled tighter together because the nucleus is getting more powerful. Yeah, exactly, because that's exactly right. Every proton has a positive charge. So hydrogen's nucleus has a charge of +1. Helium's nucleus is a charge of +2, and +2 pulls more than +1. Lithium's +3, and it just keeps going. Pulled. Sucking in power, yeah, absolutely. Not repulsion, attraction. Repulsion pushes out, attraction pulls in. Is that okay?
So the electrons are doing that because there's more in the middle? Is that what you're saying?
Yes, exactly. So you've got the so here, let's go back here. So you've got the right here. So let me just fill this all in. So the idea is, as we move across a period, we're adding protons to the nucleus. That makes the nucleus stronger, more positive, and it pulls those negative electrons tighter together.
Okay,
and therefore it makes the radius smaller. Yep. Are you guys okay? Anything else you want to explore there? All right, guys, here we go. Next trend. Right here. Got this one. We wrote that all in. Here we go, guys. This is where the logic all comes together. Trend number 4, write it down. Electronegativity. Oh, baby. You're going to like this. Electronegativity. Guys, allow me to define it for you first. Electronegativity is defined as an atom's ability to steal electrons from other atoms. So guys, if you just want to remember, it's a little bit, it's not slang, but just remember stealing power. So guys, why would we care about how able an atom is to steal? That's what allows them to bond. That's what we're going to talk about in this unit. This is important. So guys, electronegativity we are going to think of as being stealing power. So guys, what we're going to do then is we are going to talk about how this works, and then I'm going to show you. This is going to be one of your favorite Knappenberger animations of the year. You're sure to love it. Okay, so guys, stealing power depends on something called shielding. What is shielding, you ask? Well, guys, shielding is the interference that is caused by electrons surrounding the nucleus. And you're saying to yourself, I have no idea what that means. You're not supposed to. Just write it down, and I'm going to show it to you in just a minute. So guys, here's what we know. Electronegativity. What is it? Stealing power. What does it depend on? Shielding. What is shielding? It is the interference caused by electrons around the nucleus. What does all that mean? Wait and see. Tune in next time. You guys all caught up? Not yet? Lila, sorry this is so low. So guys, what are we going to do next? Arrows. Draw them in. Boom and boom. And let's go ahead and label them. Guys, there is, again, no accepted abbreviation for electronegativity, so we're just going to put EN. All right, you guys ready? We're going to turn out the lights for this one. This one's, it's touching. It's moving. It's all about stealing. Can I show you stealing? You ready for stealing? Let's talk stealing. So guys, what does it look like when atoms steal electrons? But more importantly, because remember what we're going to do is we're going to figure out a trend, right? Guys, what we really need to be able to understand is what makes atoms good stealers. You ready? Just check this out. All right, so guys, if we are going to talk about stealing electrons, certainly the thing that we need is an electron to be stolen. Do you like that it was like a little flash electron? Never. Okay, so, all right, okay, so guys, we've got an electron. And what we're going to do is we're going to play out a little game. And this is a game with a purpose, because what you need to be able to understand is what makes atoms good stealers. So if we're going to figure this out, we need to do it through comparison. So let me introduce you then to a hydrogen atom. One proton, one electron. I copied it right out of the slide where we were looking at atomic radius. Now guys, let's skip lithium, let's skip sodium, let's go down to element number, is it 19? Element number 19, potassium. Okay, so guys, here we've got a sodium atom, here we've got a potassium atom, and the question that we're going to figure out is this: which one of these is a better stealer? A hydrogen atom or a potassium atom? Now guys, in order to answer the question, you need to understand how atoms steal electrons. So guys, what's the charge of the electron? Negative. So let's look at our hydrogen atom. So guys, what part of this hydrogen atom can actually grab a hold of this electron and try to steal it? The nucleus with the proton or the electron? What's going to do the grabbing a hold? The proton. So guys, what happens is this. I accidentally touched my board. So guys, what happens is this. The proton, ready, reaches out to the electron and tries to pull it in. Huh? I know, but wait. Because guys, that's not the end of the story. The electron does try to pull in the proton does try to pull in the electron. But guys, what is this electron going to do to that electron? It's going to go, you're not coming over here. I don't want you. Now guys, don't get distracted. Listen, what is that repulsion called? No. Listen, guys, I know you're caught up in this and maybe I'm over dramatizing this and it's just distracting. But guys, listen, the proton tries to pull in the electron, but this electron is going, don't come over here, and it's pushing. And what do we call that interference caused by electrons around the nucleus? Shielding. So guys, we now have a wrestling match. This nucleus is going, hey electron, come over here, but this electron is going, you're not coming over here. You get the idea? Not now, Kat. Do you get the idea? Okay, now guys, go down here and turn your attention to potassium. Guys, 19 protons. This is a very positive nucleus. So 19 protons are going, tons of attraction, right? 19 protons. That is a huge positive charge that is wildly attractive towards electrons. But do you see the rest of the story? Guys, what are these 19 electrons doing over here? They're going, no, you don't. You're not coming over here. There's 19 of us that are saying you're not going to make the journey. So guys, now we need to think about this. Here's the question. Which one of these atoms is a better electron stealer? A weak nucleus without much shielding, or a strong nucleus with a pant load of shielding? Which one is a better stealer? Answer? They're not. It's the hydrogen. And you want to know how we know it's the hydrogen? Because it sparkles. Just a minute, please. But guys, here's the take-home message, and you need to write this down in your notes underneath electronegativity. Guys, this doesn't just work for hydrogen and potassium. There is an overarching principle here that you need to get, and it's really simple. In the world of atoms, smaller is stronger. That is universally the case. Smaller atoms are stronger atoms. The reason is because there's less shielding. But guys, smaller atoms are stronger atoms. Go ahead, Kat. What did you figure out? Yeah. Yeah, good. Brilliant. You're already looking for trends. Go ahead.
Is it also relevant to say that even atoms trying to fill its own?
Absolutely. And that, good on you. So so what's happening also, and it does apply in this case, but it also applies universally. The other thing that makes these atoms good stealers is if they can fill a shell, they will definitely try to do that. And that's actually, that's the whole point of not Monday, but Wednesday. We're going to talk about that shell filling process, which we call bonding. Yeah, just a second. You had a question? Yeah, good. It seems like a positive should cancel a negative, right? But it turns out that that's not the case. And it's for a couple of reasons. One is that this shielding actually is not always uniformly distributed. Remember, these are probabilities. And at times there's the probability that there's an abundance of electrons there that just pushes and won't let that electron in. The shielding wins because it's not truly just a balance of one proton balancing one electron. It's also about location. But the other thing that's interesting about location is it becomes about distance. It turns out that literally as we add more and more layers to the onion, the nucleus can only get so close to this electron before the shielding really becomes an issue. So really, technically, what happens is this electron, if it were coming toward the hydrogen, can get a lot closer to that one proton, and it just gets sucked in. Where here, physically, this potassium atom is so much bigger that this electron can't get close enough for it to get captured before the repulsion takes over, and it just doesn't happen. So yeah, that's a really good question. Go ahead.
So it's kind of like the electron cloud, how that's just the one electron
Yes.
that's there.
Yes.
So it can be sucked in when it's kind of the electron's kind of farther.
Absolutely. Yeah, it could be over there, and then there's no shielding at all.
The electrons and they're kind of all over.
Exactly. You got it. Okay. So guys, how you doing with electronegativity? Abby? Yes, good. We're going to do that together, but keep going. Okay? Yeah. It does. Can we talk about it in a second? Don't let us move past it. So guys, you ready? Let's come back to our big thought in blue. You sold on this? Smaller is stronger, and that's universal? You good? Okay, then guys, go back here and let me ask you a question. Why did I teach you atomic radius first? Why did I teach you atomic radius before electronegativity? Why did I teach you atomic radius before electronegativity? Exactly. It tells you the size. Isn't radius the measure of a size of a circle? And you know that as we go down, they get bigger, and as we go left to right, they get smaller. But if smaller is stronger, you also know the trend in electronegativity. Do you get it? Guys, let's write it in. So here's the idea. When we go down, they go from smaller to larger. But guys, which one is stronger, small or large? Small. So that means this will go from stronger to weaker. And then, guys, as we go from left to right, it goes from larger to smaller. So if these are larger, will they be stronger or weaker? They will be weaker, and then as we move to the right, they will be stronger. So guys, the reason I taught you the radius first is because if you understand small is strong, you also know the trend in electronegativity. So guys, let's do this first. Let's talk about the overall trend. So guys, where are the butt kickers on the periodic table? Where are the strongest elements on the periodic table, top or bottom? Hold on, think before you say. Where are the strongest elements on the periodic table? The top, left or right? Right. So guys, what should be the strongest element on the periodic table? Helium. Why isn't it? It's full. So guys, what is the strongest element on the periodic table that has room for electrons? Fluorine. And guys, fluorine kicks butt on everybody. It is, I'll show you videos. Fluorine is scary violent. It rips everybody apart. But now guys, and hear this, what is the big fat weakling on the periodic table? Bottom left, Frank. You guys, everybody beats up francium. It's really quite sad. Yeah, but realize that francium is weak because it's huge. It is so enormous that everybody just steals his electrons. Yeah, it's crazy. So guys, the trend then goes like this from weak to strong. You guys good? Go ahead. That's a great question. Can you steal an electron from a full shell? And the answer is yes, but it is crazy hard to do. Really hard to do. Yeah, to try to steal an electron from one of the noble gases is bordering on impossible. Like, it doesn't happen in nature, but we can do it in a lab. And actually the way that we do it is we take these noble gas atoms and we pulse them with X-rays, and we can get the electrons to blast off of. We're studying that in AP right now. But it doesn't happen naturally. Yeah. So guys, Abby, can we go where you're going? Guys, grab your periodic tables now and look for the electronegativities. It's on the back. It's in the upper right-hand corner. You'll notice, guys, that these numbers don't have units. They are only comparative. They allow us to say this is stronger than that. But guys, if you go, and it's the number in the upper right-hand corner, you'll notice as we go down a group, the numbers get smaller, and we go across a period, and the numbers get bigger. But Abigail is noticing that there is some fluctuation, especially in the Ds, in the transition metals, right? Guys, why would there be sort of an up and down in the D sublevel? And the reason is because electrons jump in and out of the D. They jump between the S's and the D's, and when those electrons jump, it changes the shielding and therefore the electronegativities. Remember when we did that in the last unit and we said that you shouldn't copy the noble gas abbreviations right off the periodic table because some electrons jump between the S and the D? That's also why their electronegativities change. Yeah, go. Yeah, say it again. Yep. Yeah, krypton and xenon, guys, do your periodic tables have the krypton and xenon have electronegativities? Why is that weird? They're noble gases. Why is that weird? They have a full shell. They shouldn't have anywhere to put electrons. Guys, it turns out, and again, not in nature, but in a lab, we can actually trick xenon and krypton into taking on more we can put 10 electrons in their valence shell. We overload their S and P orbitals and we force them to take electrons. They don't want to do it, but we can make them do it in a laboratory setting. It's fascinating chemistry. But understand, guys, they don't want to do that, but we can make them do it. So that's cool you picked up on that. You guys good? We got one more trend to go. You ready? The last trend that we need to talk about, guys, is what is called ionization energy. So let me define it for you. And guys, ionization energy is defined as the amount of energy needed to remove an electron from an atom. So guys, you can think of this as keeping power. How well does an atom hang on to the electrons that it's already got? Well, guys, here's the thing that's cool. The same properties that make atoms good stealers, electronegativity, also makes them good keepers, ionization energy. The trend is the same. Smaller is stronger. So guys, when we draw in the arrows and label them ionization energy, the trends are exactly the same as electronegativity. They go strong, weaker, and weaker to stronger. So guys, understand ionization energy and electronegativity are opposite sides of the same coin. Ionization energy is keeping, electronegativity is stealing. It's the same things that make them good stealers, make them good keepers. Think about greedy people. Greedy people are really good at taking in money and really bad at letting it go. You really have to work to get a greedy person to let go of money. Guys, the same thing is true here. If an atom is good at stealing electrons, it will also be good at keeping its electrons. So guys, the trends are the same. You guys good? Questions. Okay. So guys, one more thing to do. Take your sheet of paper. It's all you need about 6 or 7 or 9 more lines. Guys, we are now going to do one more thing, and we're going to wrap it up in about 4 minutes. You guys ready? Here we go. So guys, last thing we need to talk about, this is not periodic trends. This is something new. So hit the reset button in your brain, and you just need to write this down. Guys, I know that since that day in August when you bought your periodic table, you've been laying up at night, staring at the ceiling, dying to ask the question. Guys, I now give you permission to ask the question. Go ahead. No. I'll do, all right, I'll ask it for you. Why is this heavy blue line running through the right side of my periodic table? I know you've been wanting to ask. Now we can talk about it. It is actually. Guys, that line separates the metals from the non-metals on the periodic table. So guys, let's talk. The first term that you need to know, put this in your notes, is the term metalloid. So guys, a metalloid, maybe it should be plural, metalloids are the elements that are above and below the staircase. But guys, understand when we say this, it doesn't mean diagonal. So it's boron, aluminum, silicon, germanium, arsenic, antimony, beryllium, and polonium. Those are what are called the metalloids. Are they metals? Kind of. Are they non-metals? Kind of. They're in between. But guys, that's why we make computer chips out of them. Silicon, germanium. Guys, these are the two major components of computer chips because we call computer chips semiconductors. Metals conduct, non-metals don't. Metalloids are in between. And that's what makes computer chips. That's why we call them semiconductors. So guys, if the metalloids are above and below the line, the question then becomes, where are the metals and where are the non-metals? But you already know where the metals are. What do we call group 1? The alkali metals. Group 2, the alkaline earth metals. The whole D sublevel, the transition metals. Guys, the metals are on the left-hand side of the periodic table, the left side of the line. Now, what do you need to know about metals? Well, guys, there's a lot of stuff that you already know about the metals. Ready? If the metals are on the left-hand side of the periodic table, thinking about the trends that you know. Guys, check this out. I'll do it from up here. How many valence electrons do all these have? 1, and these, 2, and these, 2. So guys, metals don't have very many valence electrons. Now, looking at the trends that you know on the periodic table, if the metals are on the left, are they big or small? As we move left to right, do the elements get bigger or smaller? Oh, come on, guys. As we move to the right, they get smaller because the nucleus gets stronger, right? Atomic, you saw the smaller, right? So guys, as we move left to right, these things get smaller, so the metals on the left are big and therefore weak. Does that make sense? Okay, so guys, if they're big and weak, what are they going to want to do with electrons? Do they take them in or give them away? They give them away. And guys, these things lose electrons. And if you lose an electron, what does your charge become? Positive or negative? Positive. These things form cations. And then guys, the other things you need to know about metals, they conduct. They conduct heat and they conduct electricity. That's why we use metals as wires to conduct electricity. And they conduct heat. That's why we make pans out of metal when we cook. In addition to that, guys, metals tend to be solids. That was my next question. Guys, which so one, and did you guys pick up on this? What does black mean if the abbreviations are in black? Solid. So guys, which metals are not solids? Mercury is a liquid and hydrogen is a gas. Guys, hydrogen is a gaseous metal. And guys, these metals tend to be hard, shiny, ductile, and malleable. What on stinking earth does that mean? Well, guys, hard obviously means hard. Shiny means shiny. Guys, what does it mean if something is ductile? Do you know?
Yeah, it means that it's very.
No, it actually doesn't. It's different than that. Do you know what ductile means? Guys, have you ever seen a taffy pulling machine? You ever seen that? Or if maybe you've made taffy and you pull on it and it just gets longer and thinner, but or even silly putty. Have you ever pulled on silly putty and it just gets longer and never breaks? That means it's ductile. Ductile means it can be drawn out into a wire. And if you take metal and pull on it, it doesn't snap, it just draws out into a wire. That's what ductile means. Then malleable, guys, means smushy. If you take a piece of metal and if you bang on it, it doesn't shatter, it flattens. That's malleable. So hard, shiny, stretchy, and smushy. How about that? I know. So now, guys, let's do the nonmetals. The nonmetals are on the right-hand side. What do you need to know about the nonmetals? Well, guys, it's all the other stuff. If the nonmetals are on the right-hand side, how many valence electrons do they have? Well, they have like 8 and like 7 and like 6. They have a bunch of valence electrons. Now, guys, what about size and strength? If they're on the right, they are small and therefore strong. So they don't want to give away electrons, do they? What do they want to do? Take them in. They are electron gainers. And if you gain an electron, you don't become positive, you become negative. I'll move these up. And guys, what do we call negative ions? Anions. And then, guys, relative to the way they behave, they insulate. They do not conduct heat, they do not conduct electricity, and they can be solids, liquids, or gases, and their solids tend to be brittle. I think that's it. Yep. That was a big day. So guys, you have the homework in front of you. You'll notice that this is a multi-page adventure. It's going to stretch you a little bit to think like outside the box relative to what you just learned. You're going to be drawing pictures. Guys, when I see you on Monday, we will grade this. And then, guys, we're going to do a lab. You're going to like this one. It's probably one of my favorite labs. It's really, we're not even going to lab, and we're going to do a lab. It's fun. So, guys, make sure you get this done for Monday. I will post your test scores today, but I won't hand them back until everybody's taken it.